Thank you for introduction, and thanks organizers for the opportunity to speak on this meeting. I will start with acknowledgement of I want to thank my PhD student Zdeněk Kašpar, who did most of the measurements I will be presenting today, and also the rest of the collaborators. Okay, so today I will be speaking about mostly about this new concept Tomáš introduced in the morning. Is a new concept for storing information in degree of fragmentation in antiferromagnet, or maybe in general in magnetic materials. We call it nanotexture magnet resistance. And this new concept evolved from the concept of antiferromagnetic memories proposed 5 years ago by theoreticians, by Jakub Železný. And this antiferromagnetic memory, which was proposed by then, was based on the principle that the orientation of magnetic moments in antiferromagnet could be controlled by null spin orbit fields. And such a device would work in a way that there would be a conductive antiferromagnetic layer on top of insulating substrate, and you would create a structure in which you can send current in two perpendicular directions. And if you have correct symmetry of the crystal from which you make the antiferromagnet, you can induce these null spin orbit fields, and you can manipulate the moments and rotate them by 90 degrees. And then you read out the orientation of these moments, and you use this device to store the information. And everybody here knows about the difficulties of working with antiferromagnets. It is hard to control them with magnetic fields, and it results in the lack of knowledge about them. Like we don't know too much about anisotropies. Even null temperatures are sometimes difficult to know exactly, especially in thin films and so on. But we also have the motivation to work with antiferromagnets because they promised two big advantages. One is the exchange enhanced ultra-fast dynamics, and the other is the high storage density, thanks to the lack of dipolar interactions coming from or magnetic fields coming from the antiferromagnets. And the operation of memories based on this principle was shown experimentally shortly after the theoretical prediction or proposal. And it was shown in two materials, in copper manganese arsenide and manganese to gold. I will very quickly speak about the two experiments on copper manganese arsenide, which show this electrical control of magnetization direction in antiferromagnets most clearly. First example I want to mention is this later one from 2018. Both of these examples are based on observation of magnetic moments by X-ray magnetic linear dichroism PEEM, which is a technique which allows to determine the direction or orientation of moments. And in these pictures, black means magnetic moments in horizontal direction, and white color means magnetic moments in vertical direction. And so in this left experiment, it was shown that with electrical pulses, you can switch a domain of micron size here in the central region from one orientation to the perpendicular orientation, and then by sending the current in the opposite direction, again, you can go to white and then to black and so on. So this is single domain regime where you can manipulate the orientation of moments. And another experiment is this multi-domain regime, which was actually an earlier experiment, where you have multi-domain state of copper manganese arsenide. Again, this length is 1 micron, so this is few microns, like 5 microns in diameter. And you have domains which are smaller maybe than 100 nanometers. And you apply, in this case, there were applied pulses in perpendicular or in horizontal direction and then in vertical direction. And you cannot see too much differences. Maybe you can see here that this is darker area than this whiter. But if you subtract these two images, you get the differential image. And what you can see is that you get a complex change of the structure. But mostly you get a change of the color in one direction. So the left one is a little bit darker and the right one was a little bit brighter. And actually, our new concept of this nanotexture magnetoresistance is working mostly in this region, in this regime of multi-domain state of the copper manganese arsenide. And we believe that if we pulse even more and even more and even more and with stronger and stronger pulses, we actually enhance the degree of fragmentation in those in these in the film in such a way that the nanotextures which occur will have large contribution to resistance. And there will be 3 more talks about imaging of copper manganese arsenide domain structure, which will be touching this fragmentation regime. I will focus from now on electrical measurements of these effects. And I forgot to mention last thing. In this regime, where the experiments were focusing on the observation of reversal of or on change of the direction of magnetic moments, the electrical measurements are also done at the same time. And it's important that there there were successful measurement of AMR signals or of electrical signals which were attributed to AMR, and these resistance changes were of the order of 0.1%. And in this new concept, which we encountered, we observe effects which are 100 times stronger, which are of strength of 10% of the room temperature resistance of the material. And here I will shortly describe the structure which we are using, the device structure we are using to study this effect. Mostly we observe it in many different device structures, but this one is like the typical one. So we use this Wheatstone bridge geometry device, where we have basically 4 bars. 2 bars are horizontal, 2 bars are vertical, and we have 4 legs which connect, where we connect the electrical probes. And we can send again electrical current in horizontal direction or in vertical direction. So the black direction is black arrows indicate horizontal configuration, red indicates the vertical orientation. But now the electrical current actually, when we send the horizontal pulse, the electrical current has highest current density has current density only in horizontal bars. And when we send it in vertical direction, we have current density only in vertical bars. So basically, we are not switching the same place. We are, in one case, increasing the resistance of horizontal bars, and with the perpendicular bars, we increase the resistance of vertical bars. And this geometry is very useful because it basically measures the difference between the 2 resistances without an offset. And you also get rid of the of contact resistances. So basically, when you send a reading current in diagonal direction and you sense your voltage in this direction between these two contacts, you get signal which has this property that it is offset free, and it reflects directly the difference between the two between the resistances of the 2 couples of bars. And here we observe this the signal that when we send horizontal pulse, we change the resistance by 2 ohms. The overall resistance is actually only 20 ohms, so it's a huge change in resistance. And then the change of resistance relaxes on a time scale of seconds back to close to equilibrium value. Then we apply the perpendicular pulse. We switch to the other pair of contacts. And what we do here is we apply 100 microsecond, or we can apply pulses between 100 microseconds and 1 nanosecond and even shorter pulses. So what we do is that we increase the temperature for a very short time. The domain structure shatters into tiny domains which increase the resistances, and then we switch off the pulse and the system immediately cools down and we freeze the magnetic state which is there. And then this relaxation is actually the room temperature relaxation process. And I want to, yeah, and the strength of this effect depends obviously on the current density of the pulse. And you can see here the dependency that there is nothing happening, nothing happening, nothing happening. And then when we reach some critical current density, the effect very quickly starts to take on strength. And yeah, we observe it in single layer, simple single layer structure, but we observe it. This one is on 50 nanometer film, but we observe it on variety of thicknesses of films, and starting from let's say 20 nanometers to any thicker, and we observe it on wafers or layers grown on 3 different substrates, on gallium phosphide, gallium arsenide, and silicon, which differ in the lattice parameters. And also these wafers or these layers depend on the crystal quality. If you look at X-rays, you can see big differences. Those grown on gallium phosphide look really almost perfect crystals, while those grown on gallium arsenide are much worse. But this doesn't affect this main features of the switching we observe here at all. It seems it's not related to. From this, it seems it's not related to defects or whatever. It's really related to the main phase of copper manganese arsenide. And yeah, basically, the strength is 10%. It's too strong for AMR picture, but still, one could in this geometry one could still think, okay, maybe we start with random orientation of domains and we just polarize them temporarily with the electrical pulse. In one case, in one direction, in the other case, the other bar in the other direction. So apart from the fact that it's too strong effect for AMR, it could still be AMR. And to be completely sure that this is not the case, we did the experiment with optical pulses, with laser pulses, where we take the same structure and we apply a laser pulse, which has length 100 femtoseconds. That's just because we had at hand 100 femtosecond laser. And it delivers energy of 1 nanojoule into area approximately 1 micron squared. And we hit it to the structure. And when we hit it into vertical bar, we will induce switching with positive sign and with the same relaxation as we observed this for the electrical signal. When we hit the laser to the horizontal bar, we get a negative signal. Then we can apply multiple pulses. This is 1 to 600 pulses, and we increase the strength of the signal. And we can also scan with the laser in the area of the bar to increase the signal. So it means that we are basically having exactly the same signal coming from the electrical writing, like from the optical writing, which really proves that the orientation of moments is not important in this effect. The only thing which is important is this internal property or this internal parameter of order, determining the order of the domain structure or nanotexture. Yeah, and another thing which is very interesting is that we observe very regular relaxation, and it's actually sort of fingerprint of this effect. Maybe this relaxation can be used really to separate this effect from maybe the AMR related effects, which do not relax or maybe relax differently. But what we observe is that at room, I don't have here temperature. This is relaxation at room temperature. This is relaxation at 280 kelvins, and this is 320 kelvins. So basically, the relaxation is quickly changing with temperature. And we found out that we cannot fit this relaxation with simple exponential functions, but we can fit it perfectly with stretch exponential functions with exponent 3/5. And it actually sort of makes sense because the standard exponential relaxations are related to phenomena for which the properties of individual elements which are isolated from environment are the key properties. And what so this would correspond, for example, to some small piece of ferromagnet which would relax from one state to another. Then it would behave in a exponential way. But whenever there are many elements of similar properties which are in fact interacting and together, and which needs this, and when this interaction becomes strong, these stretched exponentials start to describe the system. And the interesting thing is that the stronger is the interaction and the more complex is the interaction, the better fit one obtains with the stretched exponentials. And so they are used for description of different phenomena in physics, but also in biology, in economy, everywhere. And the only condition for them to work is really that the system is complex. And in fact, we found that this 3/2 exponent we observe is sort of seen or typical in 3D systems with complex interactions. So that's actually sort of even this is working. And once you can fit these relaxations, you can obtain the relaxation time, and you can do it at different temperatures. And when we analyze the temperature dependency of the relaxation time, we can extract the activation energy of the relaxation process and the attempt rate or the characteristic time. And what we found is that the attempt rate is 1.6 terahertz, which basically points to the idea that really what is in the core of these processes could be antiferromagnetic dynamics. Yep. Now we are ready for this almost last thing I want to mention. We can construct very simple device using this principle. We can just take a bar of copper manganese arsenide and connect it in two-point resistor configuration. And then when we send writing electrical pulse, which has current density 10 to 7 amps per centimeter square, we change the resistance by 4 ohms, and then it relaxes a little bit, and then we can send a smaller pulse, which increases the temperature to a little bit lower value than the writing one. It's 90% of the current density of the setting pulse, and it actually resets the state to much lower value. And we can understand this process quite easily now because we already know that this relaxation is very temperature dependent. And so basically, when we are writing, we not only go to temperature where the domains are small, but we also increase the rate at which the domain structure is changing. And so basically, when we, with first pulse, increase the domain density into very high value and freeze it, and then with the second pulse, we deliver just enough heat to actually allow the relaxation of this frozen state to intermediate state, we can, in fact, quite effectively, in one device, set the high resistance value and then go quite close to the low resistance value and then up again and so on. And so this is actually the simplest possible operation configuration, how you can operate memory, because you actually send electrical pulse through one 2-point resistor, you change it by tens of %, you change the resistance by tens of %, and you can reset it by applying pulse in the same direction, only 10% weaker. Yeah, and then last thing I want to mention is the temperature dependency of the switching signal. It's quite challenging to do the switching at different temperatures because you need to apply different current density, and then it's difficult to compare the strength of the switching signal at one temperature with strength of the switching signal at different temperature. But what we could do was that we could apply the switching pulses at 250 kelvins when the relaxation is already slow, and the relaxation times is in the order of tens of minutes. And then we can apply the pulse and very quickly cool the cryostat down to 50 kelvins where the relaxation is completely stopped. And then we can measure for 20 minutes at 50 kelvins, measure for 20 minutes at 100 kelvins, 150 kelvins, 200 kelvins, and then 20 minutes at 250 kelvins, we see already the relaxation. So by this procedure, we obtain the resistance for all temperatures in this range, and for the same state. And what it is showing us actually is that we can change the resistance from 5 ohms to 2.5 ohms. And I forgot to mention, now we are measuring in longitudinal geometry, so we are not measuring the difference of the two resistances, but we are really measuring only resistance of horizontal bars, of the two horizontal bars. And we can really change it by factor of 2. And so it means that actually this scattering on this magnetic disorder is of the order of residual low temperature resistivity of copper manganese arsenide. And this is a place where we can connect a little bit to existing ab initio calculations. There is a theoretical paper which was published 2 years ago. It is completely independent of this study, but they mentioned they are trying to calculate influence of various defects in this material on conductivity, but they also mentioned that if they calculate the resistance of antiferromagnetic state, perfectly ordered antiferromagnetic state, and then they take completely random orientation of moments and freeze them to low temperature and keep them frozen in random orientations, they will obtain factor of 3 higher resistivity. And so basically it is sort of consistent with what we observe here, that by significant, well, by the strongest pulses we dare to use, we can obtain really that strong change in resistivity as well. So I will summarize the properties of this nanotexture magnetoresistance I was trying to describe. We see large resistance change. One very important thing is that this effect is possibly universal for all conductive antiferromagnets, because we don't have anymore this requirement on crystal structure, which was originally needed for the Nel spin orbit switching. Again, it is observed in simple single layer structure. It can be operated in this simplest possible 2-point resistor configuration, and we can operate it with writing and resetting electrical pulses in the same direction. We have the multi-level characteristics, and we have very nice and regular relaxation at room temperature, which maybe leads to promising applications in neuromorphic computations, which we will hear about in next talk by Xavi. Thank you for your attention.